So this is part 2 of chapter 14. We had left off here on the industrial synthesis of ethers. Moving forward. So in terms of examples of industrial synthesis of ethers, here are a couple of examples. Here's N-propyl alcohol, sulfuric acid, high temperatures, N-propyl ether. Isopropyl alcohol, again sulfuric acid, high temperatures. You get unimolecular dehydration in this case, no ether is formed. You can cleave ethers by adding HBr or HI. In general, ethers are unreactive, which makes them ideal solvents for a lot of different reactions. However, they can react by cleavage reaction in the presence of concentrated HBr or HI in the presence of high heat. In general, the reactivity is HI is favored, followed by HBr. In terms of mechanism of ether cleavage, first step is protonation with in this case, HBr, the acid. This will generate the protonated ether and the anion. That halide will then attack the carbon on one of the alkyl groups. Electrons will go to the oxygen, forming the alcohol and forming the alkyl bromide in this case. So that alcohol that is formed then reacts with another equivalence of HBr to generate the alkyl halide and water. So 2 moles of alkyl halide is then formed, and this does not, that's really important, does not occur with aromatic alcohols or phenols. In terms of phenyl ether cleavage, phenols cannot react further to become a halide because an SN2 reaction can't occur on an sp2 carbon. So if we look at this here, reaction of a ethyl phenyl ether in the presence of hydrogen bromide protonates that bromide, anion forms, that bromide anion then attacks this ethyl group, electrons go to form the phenol and then ethyl bromide. After you form the phenol, you don't have another equivalence of HBr reacting, rather no further reaction occurs. Important thing to note is that HBr and HI convert both alkyl groups, but not aromatic groups, of an ether to an alkyl halide. Phenolic products are unreactive, however. Ethers can undergo auto-oxidation. In the presence of atmospheric oxygen, ethers slowly oxidize to hydroperoxides and dialkyl peroxides. Both are highly explosive, so you want to take precautions and not distill ethers to dryness and store in full bottles with tight caps. In terms of the mechanism of auto-oxidation, you have your ether in the presence of excess oxygen. You'll form the hydroperoxide, where essentially on this methylene group you actually add the OH, or in the presence of the ether you add another oxygen, insert another oxygen to form the dialkyl peroxide. So if you have, for example, diisopropyl ether in the presence of excess oxygen, weeks or month, note the time frame because it's a slow reaction, you're going to generate the hydroperoxide again where the OH is on the methylene, or the CH over here, substituting the CH there, or the diisopropyl peroxide in which another additional oxygen is added to the system. In terms of thioethers, the RSR, instead of an oxygen, you have a sulfur here. That's the analog of an ether. You essentially name sulfides like ethers by replacing sulfide for ether or alkyl for alkoxy in the IUPAC system. Here are examples below. This is dimethyl sulfide, methylphenyl sulfide, and 4-ethyl thio 2-methyl pentuene. So shown here. right? So this is the longest chain. Thiols and thiolates. So if you take a thiolate, you can react it with an alkyl halide. So like an alkoxide, the thiolate will then react SN2 to form ethyl propyl sulfide, in this case, and the bromine. So it's using the same protocol of Williamson ether synthesis, instead using a thiolate as the nucleophile. In terms of sulfide reactions, sulfides are easily oxidized to sulfoxides and sulfones. So here's dimethyl sulfide in the presence of hydrogen peroxide and acetic acid. You oxidize that sulfur group, right, once in the presence, again, of more hydrogen peroxide and acetic acid. You generate the overoxidized form. So the sulfone, so this would be the sulfoxide, this is the sulfone, so remember those names. Sulfides react with unhindered alkyl halides to give what are called sulfonium salts. So in the presence of dimethyl sulfide and methyl iodine, you'll have a nucleophilic attack in which electrons, right, here's your sulfur, electrons attack, kick off to form the sulfonium salt shown here. Thioethers can also be used as reducing agents. So if we look at the example here, we're oxidizing using one of the reagents we learned about last semester, ozone. Ozone will form as ozonide in the presence of, right, dimethyl sulfide. Now, when we were learning this reaction, dimethyl sulfide comes along and will react, right, with nucleophilically to generate dimethyl sulfoxide. So sulfides are easily oxidized. They're often used as mild reducing agents in this reaction. In terms of mechanism, as we've discussed before, again, electrons go here, this will form double bond, this will form double bond, this will go back to the sulfur to form the dimethyl sulfoxide, and then here in this case, the dioxidized state. Silyl-ethers. So we've talked about ethers, thioethers, and silyl-ethers are as such here, right? So you have a silicon group next to an oxygen of the alkoxide here. These are resistant to some acids, bases, and oxidase agent. They're more easily formed and more easily hydrolyzed. They're used as protecting groups for alcohols, shown here. So this would be an alcohol, and this would be the protecting group. So if we look at a reaction and why alcohol protecting groups would be needed, here would be, right, a reaction in which you want to generate a Grignard reagent. So here you're adding the Grignard, right, in the ether, and you're hoping to actually use this to attack this ketone, but it isn't formed. The reason why it isn't formed because this will deprotonate in the presence of phenylmagnesium bromide as a result of forming the alkoxide. So if your molecule has more than one functional group, sometimes the reactivity can interfere with the desired reaction as shown here. So silyl-ethers can serve as protecting groups on alcohols. So you can use chlorotriisopropylsilane, and in the presence of the alcohol, electrons will go, kick off the chlorine, forming the protected alcohol shown here. This can be deprotective in tetrabrutyl ammonium fluoride, shown here, and so the fluorine will kick this off to regenerate the alcohol. So you can then protect the alcohol as a silyl-ether, so that will ensure the Grignard will react with the carbonyl group in the previous case, and then you can remove that silyl-ether group in aqueous organic solvent. Sulfonium salts can also serve as alkylating agents. So if you have a nucleophile that can attack, here's your sulfonium salt. Electrons get pushed back. So this is a SN2 reaction. So then you formed, right? You've just alkylated with this methyl group onto this nucleophile, forming the sulfide and your halide. So as an example, here's pyridine. Pyridine is your nucleophile. Will take off that methyl group from this trimethylsulfonium iodine, quenching that to form the dimethyl sulfide and the N-methyl pyridinium iodide. So you can use these as alkylating reagents, these sulfonium salt, because the leaving group that is formed is going to be neutral. Epoxides, as we've seen before, you can react alkenes with peroxy acids to form epoxides and the acids. So the most common type of peroxy acid is peroxybenzoic acid, which we talked about last semester. Reaction is carried out in aprotic acid to prevent opening of the epoxide. So the selectivity of epoxidation. So in general, you form on one side of the double bond. So in this case, in the presence of MCPBA, one equivalent, you generate the 6,4,5 epoxy dimethyl cyclohexene in this case. Here's the E. Again, it'll just go on top, and you'll generate the E-methyl nitrophenyloxyrane shown here. Most electron-rich double bonds react faster in general, making selective epoxidation possible. So if we had the choice between here and here, this is more electron-rich. As a result, only this one, if you use one equivalent, gets oxidized to the epoxide. And this is another epoxidizing reagent, MMPP. Halohydrin cyclization. So once you add OH and X, you can do that across a double bond. So if we had a double bond, we can react that with, for example, X2 and H2O. Sorry, my handwriting is a bit bad here. Then you can generate the halohydrin, and then in the presence of base, in this case hydroxide, it'll deprotonate, allowing for kind of this SN2, internal SN2 reaction so that you form the epoxide. You can, so here are more examples of epoxides via halohydrin. Again, from the double bond, right, in the presence of, this is dichloride water, you form the halohydrin. So shown here is the reaction. You form the chloronium ion as we had shown before. And once the chloronium ion is formed, then the water attacks one side, kicking off the electrons to the chloride to form the trans-chlorohydrine. And in this case, you get a mixture of enantiomers, as we've discussed in the previous semester. Once you generate that halohydrin, then you can react it with, this is base, deprotonate that proton over there of the hydroxide. Electrons go here. Once the electrons are here, then you have SN2. The alkoxide forms nucleophilic attack, forming the epoxide. You can also perform acid-catalyzed opening of epoxides. So once you generate the epoxide in the presence of acid, and this is a hydronium ion, electrons will pluck off that hydrogen, forming the protonated epoxide. Then the step 2 is that the water will then attack the protonated epoxide on one side. Electrons will go, forming, right, the OH-OH2. Water will come here, deprotonate, so that neutralizes it. So now you have this trans-diol after the deprotonation. So you can also have acid-catalyzed opening of epoxides in alcohol solution. So when that happens, you form an ether, as shown here. You can have, again, the epoxide protonates, right? You have the protonated epoxide. Then you have, instead of water, alcohol come in. This is methanol. Tack one side, kick electrons off to the oxygen. Now you have this protonated alcohol, right, attached. You want to remove that proton. Another equivalence of methanol will come in, remove that proton, generating now the 2-methoxycyclopentanol. Again, it's trans. So this will form an alcohol with an anti-stereochemistry. In general, for proposing mechanisms for acid-catalyzed opening of epoxides, imagine that the protonated epoxide opens to the more stable or more substituted carbocation. That's important. So if it opens to the more stable carbocation, then that carbocation will be what is attacked with the nucleophile. Base catalyzed openings of epoxides, instead of protonating, what happens is the base comes in. Oops, sorry, I'll just not use that. And then attacks and then opens the ring, right? So now you have an alkoxide. The diol is obtained after you protonate this alkoxide with water. If we look at ring opening in base, right? So if we took a general ether, having that nucleophilic attack, and then cleaving that to generate the alcohol and the alkoxide, that requires really high activation energy. However, the epoxide produces ring strain, and as a result, you have it starts at a higher energy because of the ring strain, and a lower activation energy to get to the product, the product here. So epoxide is approximately 25 kcal per mole higher in energy due to this ring strain. The release of the ring strain makes the opening of epoxide thermodynamically favored versus this one in the non-ring strain system. Ring openings with hydrohalic acid, so you can use HX, right? Hydrohalic acid, again, it gets protonated, X is here. Once it's protonated, the X will come in, attack one side, open up the ring so that you generate the halohydrin. Again, you can react it with another equivalence of HX, in this case, what happens is you have the electrons from the oxygen attack the HX, breaking the bond between H and X, and then once you form, so I'm going to draw the intermediate, OH. Sorry. Please bear with my awful handwriting here, but you get the point. So here's your intermediate, shown here, where you have a positive charge now on the water because it's just protonated from the HX, and then the X will come in and attack and kick that off so that you generate two halides. So you get a 1,2-dihalide. In terms of reactions of epoxides under either acidic or basic conditions, in the case of acidic conditions, the alcohol will attack the most substituted side. That's because you form a partial buildup of positive charge over here. In the case of basic conditions, right, here's the alkoxide and ethanol. Now this will attack the least substituted side, opening up the ring. So the base catalyzed product reacts on the least substituted side. The acid catalyzed product reacts on the most substituted side. So let's do a problem. It says predict the major products for the reactions of 1-methyl-2-epoxycyclopentane with sodium methoxide and ethanol and H2SO4 and ethanol. In the case of sodium hydroxide or sodium ethoxide and ethanol, what happens is it'll attack the least substituted side, ring open. So it'll give you the E2-ethoxyl-methylcyclopentanol, right? Once it ring opens, then you protonate using the ethanol. Under acidic conditions, the alcohol attacks the more electrophilic tertiary carbon of the protonated epoxide. So once it protonates, this builds up a positive charge. So I'm going to show partial positive charge over here. As a result, your ethanol will attack that positive charge, open, so you generate the E2-ethoxy-2-methylcyclopentanol. Here's an example of the biosynthesis of steroids. Here's squalene. Squalene, this happens in cells. Squalene, in the presence of squalene, epoxidase, which is an enzyme, will epoxidize, right, this position at the 2,3 position to generate squalene 2,3 epoxide. Then this undergoes reaction so that the electrons will start moving. So here's your electrons. It starts moving to close the ring here to here to here and then to here, and opening that epoxide up to generate the cyclized intermediate. This then undergoes several transformations to form lanosterol and then cholesterol, which is what you guys know. Reactions of epoxide with Grignards and organolithiums. We've talked about this before. Here's an epoxide in the presence either Grignard or organolithium. It'll react on the least substituted side, so it'll react here, and opening it up. So like in the basic case, these are strong bases. You're going to open up the epoxide and the less hindered carbon. So that ends chapter 14.